Electrical engineering encompasses a vast range of concepts and applications. At its core, it deals with the study and application of electricity, electronics, and electromagnetism. It's a field that has shaped the modern world, powering our homes, industries, and technologies. One of the fundamental concepts in electrical engineering is the electric circuit. An electric circuit is a closed loop that allows electric charge to flow. This flow of charge is known as electric current, measured in amps. For a circuit to function, it needs a source of electrical energy, such as a battery or a power supply. This source provides the voltage, which is the electrical potential difference that drives the current through the circuit, measured in volts. Circuits also contain components that control and utilize the current. Resistors, for instance, impede the flow of current, converting electrical energy into heat. The amount of opposition to current flow is called resistance, measured in ohms. The relationship between voltage, current, and resistance is described by Ohm's law, a cornerstone of electrical circuit analysis. Ohm's law states that voltage equals current times resistance. Mathematically, it is represented as volts equals amps times ohms. This simple equation is incredibly powerful, allowing engineers to calculate current, voltage, or resistance in the circuit if the other two values are known. For example, if a circuit has a 12-volt source and a 6 ohms resistor, the current flowing through the circuit would be 2 amps. This is because 12 volts divided by 6 ohms equals 2 amps. In more complex circuits with multiple components, Kirchhoff's laws are essential. Kirchhoff's current law, often abbreviated as KCL, states that the total current entering a junction or node in a circuit must equal the total current leaving the junction. In other words, current cannot be created or destroyed at a junction. It's a statement of conservation of charge. Kirchhoff's voltage law, abbreviated as KVL, states that the sum of the voltage drops around any closed loop in a circuit must equal 0. This is a statement of conservation of energy. As current flows through resistors, voltage drops occur, and the sum of these voltage drops around a closed loop must equal the voltage supplied by the source. These two laws, KCL and KVL, allow engineers to analyze and solve complex circuits with multiple branches and loops. Another important concept in electrical engineering is power. Electrical power is the rate at which electrical energy is transferred or consumed in a circuit. It's measured in watts. The power dissipated by a resistor is equal to the voltage across the resistor times the current flowing through it. Mathematically, power equals volts times amps. This formula can also be expressed in terms of resistance using Ohm's law. Since volts equals amps times ohms, we can substitute this into the power equation to get power equals amps squared times ohms. Similarly, since amps equals volts divided by ohms, we can substitute this into the power equation to get power equals volts squared divided by ohms. These different forms of the power equation are useful depending on which values are known in a circuit. Understanding power is crucial for designing efficient and safe electrical systems. Engineers must ensure that components are rated to handle the power they will dissipate to prevent overheating and failure. So far, we've discussed direct current, also known as DC circuits, where the current flows in one direction. However, alternating current, or AC, circuits are also prevalent, especially in power distribution systems. In an AC circuit, the current changes direction periodically. The voltage also alternates polarity. The most common waveform for AC voltage and current is a sine wave. The frequency of an AC signal is the number of cycles per second, measured in Hz. In the United States, the standard frequency for AC power is 60 Hz. When analyzing AC circuits, it's important to consider the concept of impedance. Impedance is the AC equivalent of resistance. It takes into account not only resistance but also the effects of capacitors and inductors. Capacitors store electrical energy in an electric field, while inductors store electrical energy in a magnetic field. Both capacitors and inductors oppose changes in current and voltage respectively. This opposition is called reactance, and it's frequency dependent. The total impedance of an AC circuit is the vector sum of resistance and reactance. The impedance is measured in ohms, similar to resistance. The relationship between voltage, current, and impedance in an AC circuit is described by a modified form of Ohm's law. In this case, voltage equals current times impedance, where all three quantities are complex numbers. Analyzing AC circuits requires the use of complex numbers to account for the phase relationships between voltage and current. Power in AC circuits is also more complex than in DC circuits. In addition to real power, which is the power dissipated by the load, there is also reactive power, which is the power stored and released by capacitors and inductors. Reactive power does not do any useful work, but it does contribute to the overall current flow in the circuit. The total power in an AC circuit is called apparent power, which is the vector sum of real power and reactive power. The power factor is the ratio of real power to apparent power. It's a measure of how efficiently electrical power is being used. A power factor of 1 indicates that all the power is being used effectively, while a power factor less than 1 indicates that some of the power is being wasted due to reactive components. Electrical engineering also involves the design and analysis of electronic circuits. Electronic circuits use components such as transistors, diodes, and integrated circuits to perform a variety of functions. Transistors are semiconductor devices that can be used as switches or amplifiers. Diodes are semiconductor devices that allow current to flow in only one direction. Integrated circuits, also known as chips, are complex circuits containing millions or even billions of transistors and other components on a single silicon die. Electronic circuits are used in a wide range of applications, from computers and smartphones to industrial control systems and medical devices. Digital electronics deals with circuits that operate on discrete values typically represented by 0 and 1. These circuits are used to perform logical operations and store data. Analog electronics deals with circuits that operate on continuous signals. These circuits are used to amplify signals, filter noise, and perform other signal processing tasks. The design of electronic circuits requires a deep understanding of semiconductor physics, circuit theory, and digital logic. Electrical engineers also work with electromagnetic fields. Electromagnetic fields are created by electric charges and currents. They are responsible for a wide range of phenomena, from radio waves and microwaves to light and X-rays. Electromagnetic compatibility, or IMC, is an important consideration in the design of electronic devices. EMC ensures that devices do not interfere with each other and that they are not susceptible to interference from external sources. Electrical engineering also plays a vital role in power generation, transmission, and distribution. Power plants generate electricity using a variety of sources, including fossil fuels, nuclear energy, and renewable energy sources such as solar, wind, and hydropower. The electricity generated at power plants is transmitted over long distances using high-voltage transmission lines. These transmission lines are part of the power grid, a complex network of interconnected power plants and transmission lines. The high-voltage electricity is then stepped down to lower voltages at substations before being distributed to homes and businesses. Electrical engineers are involved in all aspects of the power grid, from designing power plants to developing smart grid technologies. Smart grids use advanced sensors, communication networks, and control systems to improve the efficiency, reliability, and security of the power grid. They also enable the integration of renewable energy sources and the use of electric vehicles. In addition to these core areas, electrical engineering also encompasses many specialized fields such as control systems, signal processing, communications, and computer engineering. Control systems are used to regulate the behavior of dynamic systems such as robots, aircraft, and industrial processes. Signal processing is used to analyze and manipulate signals such as audio, video, and images. Communications deals with the transmission and reception of information over communication channels. Computer engineering combines electrical engineering and computer science to design and develop computer hardware and software systems. These specialized fields require a deep understanding of the underlying principles of electrical engineering, as well as specialized knowledge in their respective areas. Electrical engineering is a constantly evolving field, with new technologies and applications emerging all the time. As technology advances, electrical engineers will continue to play a vital role in shaping the future.